In the mid-20th century, aviation was a sensory experience not just for the passengers, but for the crews. Maintenance was visceral. If an engine was running hot, a flight engineer didn't get a digital notification. He watched a physical needle quiver against a red line on a dial. He listened for the subtle change in the mechanical hum, so to speak, of the turbine. He looked for a faint trail of blue smoke or the smell of hydraulic fluid in the vents. His experience was the onboard maintenance system. But as we pushed aircraft into the supersonic age and then into the era of ultra-efficient high-bypass turbofans, the machine became too complex for any human to feel its heartbeat. Today, the modern jetliner is essentially a flying server farm. We've traded the flight engineer's intuition for the digital witness, the Onboard Maintenance System, or OMS. To give you an idea of the scale we're talking about, a single 10-hour flight of a modern twin-aisle aircraft can generate upwards of 500 gigabytes of data. That's not just video or audio, that's millions of discrete data points, valve positions, fuel flow rates, voltage fluctuations, and even the micro vibrations of a bearing deep within the engine core. No human mind can process that in real time. We need a system that could not only watch everything, but understand it. The philosophy of OMS is built on three historical pillars of maintenance evolution. First, there was reactive maintenance. This was the fly-to-fail model. You fixed it when it smoked, leaked, or snapped. It was dangerous and incredibly expensive. Then came the preventative maintenance. We decided that every 1,000 hours we would replace a part regardless of its condition. It was safer, but wasteful. We were throwing away perfectly good components. Today, the OMS has ushered us into the era of condition-based maintenance. The aircraft now has the self-awareness to say, I'm not broken yet, but based on the vibration levels in my number 2 fuel pump, I will likely fail in 48 flight hours. This isn't just a convenience for the mechanics. It's the backbone of modern airline economics and safety. In this video, we're going to look at how this digital consciousness works, from the microscopic sensors in the wings to the satellite arrays that beam this data across the globe before the wheels even touch the tarmac.
To understand how the aircraft knows it is sick, we have to look at the cells of the system, the line replaceable units, or LRUs. Inside almost every electronic box on a plane, from the flight control computer to the coffee maker in the galley, resides a dedicated piece of software known as the BITE, or built-in test equipment. BITE isn't just a simple on-off check. It is a multi-layered diagnostic protocol that operates in 3 distinct, rigorous modes. Let's break those down. The first is the PBIT, or Power-Up BITE. Think of this as the aircraft's morning stretch. When the ground crew applies power to a cold aircraft, the BITE performs a series of destructive and non-destructive tests. It flashes its own memory to check for corrupted code. It sends a surge of voltage to its sensors to see if they respond within a tolerance of a nominal limit. It cycles solenoids to ensure they aren't seized. If the PBIT fails, the LRU flags itself as inoperative before the passengers even board. Secondly, the CBIT, continuous BITE. Once the plane is in the air, the CBIT takes over. This is a silent observer that runs in the background often hundreds of times per second. It uses a technique called wraparound monitoring. If the flight control computer sends a signal to move an aileron by 5 degrees, the CBIT immediately checks the feedback sensors on that aileron. If the sensor reports back, for example 4 degrees instead of 5, the BITE knows there is a discrepancy. It doesn't just ignore it, it starts a timer. If that discrepancy lasts for more than say 200 milliseconds, a hard fault or confirmed fault is born. Finally, we have the SBIT, or System BITE. This is a doctor's exam. This mode is only accessible on the ground by active ignition. Through a maintenance terminal, a mechanic can command a system, like the landing gear hydraulics, to perform a sequence of movements to measure pressure decay or response times. It is a deep dive diagnostic that allows the human to interrogate the machine. But a fault message is useless without context. This is where the freeze frame comes in. When a BITE detects a failure, it triggers a data dump of the surrounding environment. It records the timestamp down to the microsecond, the flight phase, was the plane climbing, cruising, or landing, the environmental data, what was the outside air temperature, what was the cabin pressure, and the electrical state, was there a voltage spike on the main bus at the exact moment. By capturing this freeze frame, the OMS allows engineers to recreate the exact conditions of a mid-air glitch where the plane is safely sitting in a hangar. It removes the guesswork and ensures that when we replace a part, we're replacing the correct part.
If the BITE is the witness, the central maintenance computer, CMC, is the detective. In a modern glass cockpit aircraft, systems are so deeply integrated that a single hiccup can cause a fault storm. Without a filter, a pilot would be bombarded with hundreds of warnings, most of which are just symptoms of a single root cause. The CMC's primary mission is fault, correlation, and consolidation. Think of the CMC as a high-speed librarian that also happens to be an expert on the airplane's blueprints. It uses something called inhibit logic. For example, the CMC knows that during the high-stress takeoff phase, the pilot doesn't need to know if a reading light in row 24 is broken. It suppresses non-critical data to keep the human in the loop focused on flying. But behind the scenes, it's building a massive logical map. Let's have a look at the logic tree. When a bird strike impacts a pitot tube, the sensor that measures airspeed, the failure propagates instantly. The autopilot disconnects because it doesn't know how fast it's going. The flight management computer throws an error. Even the landing gear system might report a fault because it uses airspeed to determine if it should allow the wheels to retract. The CMC looks at the global timestamp of every message. If 50 faults occur within a 100 millisecond window, the CMC applies its hierarchy. It asks, which system is the provider and which is the consumer? By tracing the signal back to the provider, it realizes the pitot tube is the only true failure. It suppresses the 49 symptom messages and tells the mechanic exactly what to replace. The system categorizes each fault into one of three classes: Class 1 are the active faults. These are the red and amber alerts. They have a direct impact on the current flight's safety or operational capability. These are sent to the ICAS or ECAM screens immediately. Class 2 are the maintenance alerts. These are faults where the plane can still limp home. This means the plane is safe to fly the current leg, but it cannot take off again until the part is replaced. The CMC flags these so the airline can reroute the plane to the hub with the spare part. Class 3 are the latent faults. These are the invisible failures. Modern planes have triple redundancy. If the third string backup sensor fails, the plane is still 100% safe, but the CMC still logs it. It's a hidden failure that will be addressed during the next scheduled overnight check, preventing a future Class 1 event.
Data is the lifeblood of maintenance, but that blood has to travel to the airplane's nervous system. In the early days of digital avionics, the era of Boeing 757 and 767, we relied on ARINC 429. It was revolutionary for its time, but it was a point-to-point system. If a sensor wanted to talk to 3 different computers, you had to run 3 separate pairs of copper wires. ARINC 429 is slow by modern standards, topping out at 100 kilobytes per second. It is incredibly reliable because it is simple. But as planes got smarter, the weight of all the copper wiring started to hurt the airline's fuel bottom line. We needed a faster, lighter way to move the massive diagnostic files generated by the OMS. Enter AFDX, or Avionics Full Duplex Switched Ethernet. If ARINC 429 was a walkie-talkie, AFDX is high-speed fiber optic internet. Used in the Airbus 380 and the Boeing 787, it moves data at 100 megabytes per second. That's 1,000 times faster than the previous generation. But there's a catch. In your home Wi-Fi, if everyone starts streaming 4K video, the network slows down. In an airplane, a delay of even a few milliseconds in the flight control signal could be catastrophic. This is why AFDX is deterministic. Engineers use virtual links to create guaranteed lanes for data. The OMS is programmed with a quality of service mandate. A critical message about an engine fire or a wing flap jam is guaranteed a lane that can never be blocked by lower priority data, like the temperature of a galley oven. This allows the OMS to transmit high-definition health packets to ground stations via satellite while the plane is still at 35,000 feet, without ever compromising the safety-critical systems.
The engines are the most expensive and complex assets of the aircraft. They are also the most vocal. Through the Engine Health Monitoring, EHM, the OMS becomes a digital cardiologist, listening to the engine's rhythm through 3 primary metrics: N1, FF, and EGT. N1 measures the rotational speed of the front fan. It is the primary indicator of the thrust being produced. FF, standing for fuel flow, measures the rate of fuel consumption. A sudden increase in fuel flow to maintain the same thrust can indicate a drop in engine efficiency. EGT, which is short for exhaust gas temperature, measures the temperature of the gases exiting the turbine. This is the most critical measure of the internal health of the engine. The most critical parameter in engine maintenance is the EGT margin. Every engine has a red line, a maximum temperature it can reach before the internal alloys begin to degrade. When an engine is brand new, it runs very cool. But as the blades get tiny microscopic nicks from dust and sand, the engine has to burn more fuel to create the same thrust, making the EGT rise. The OMS uses trending algorithms to watch this rise. It doesn't care about a single hot takeoff in Dubai. It looks at the rolling average. Imagine the OMS sees the EGT margin shrinking each week. It applies a predictive AI to the curve. Therefore, it can forecast that in exactly 54 days, the engine will cross the threshold where it's no longer efficient. Instead of waiting for an engine to fail, which could cost an airline 50 million in emergency repairs and lost revenue, the OMS triggers a prognostic alert. The airline schedules a water wash to clean the blades or a bore scope inspection to check the wear. This turns a potential disaster into a routine 3-hour maintenance task. This is the power of the OMS. It's the difference between being a mechanic who reacts to a broken machine and an engineer who manages a healthy one.
We have explored the sensors, the logic gates, and the high-speed data buses, but data alone doesn't fix an airplane. The final and most critical component of the onboard maintenance system is the human interface. In the 1990s, a mechanic carried a stack of heavy paper manuals. Today, they carry a gateway into the aircraft's soul. This is the OMT, or Onboard Maintenance Tool. It is no longer just a screen in a cockpit. Through secure wireless gate-link technology, the aircraft begins talking to the technician's tablet the moment it enters the aircraft's geofence. By the time the engines are shut down, the mechanic has already reviewed the last leg's performance and is looking at a prioritized list of tasks. One of the most powerful features in the modern OMS is its integration with the FIM, or Fault Isolation Manual. In the past, a fault code like 21, 23, 45 would require the mechanic to manually flip through thousands of pages of diagrams to find the right troubleshooting tree. Now, the process is instantaneous. The technician taps the fault on the screen and the OMS provides a guided troubleshooting. It says, based on this fault, there's a 90% probability the problem is the pressure regulation valve. Here's the part number, here's its location in the aft bay, and here the 3D wiring diagram. It even checks the airplane's live inventory to see if the part is in the hangar. This isn't just maintenance. It is a surgical strike against downtime. In 2026, as aircraft becomes more connected, the biggest threat isn't mechanical wear. It is digital intrusion. The maintenance access point is a high-security node. If a hacker could access the OMS, they could, theoretically, spoof fault data or even alter system configurations. To prevent this, aviation engineers use a concept called domain isolation. The aircraft is divided into islands. The passenger information and entertainment service domain, the Wi-Fi you use for Netflix, is physically and logically separated from the aircraft's control domain. Crucially, the OMS uses data diodes. These are hardware devices that allow data to flow in only one direction. The flight computers can send health data out to the maintenance tablets, but the tablets cannot send commands back into the flight control unless a physical write enable switch is toggled by a human in a cockpit. Combined with multi-factor authentication and encrypted ARINC 664 protocols, the airplane's brain remains a fortress. Looking ahead, the OMS is evolving into a self-learning entity. We are moving beyond simple logic trees into neural networks. By analyzing data from 10,000 different aircraft across millions of flight hours, AI can now spot pre-fault signatures, vibrations so subtle that no human sensor could detect them, and predict a failure months before it happens. The onboard maintenance system has fundamentally changed our relationship with flight. It has turned the airplane from a passive machine of metal and kerosene into an active participant in its own survival. It is a silent guardian that never sleeps, never blinks, and never forgets. The next time you settle into your seats and hear the engines roar to life, listen closely. Beneath that roar is the whisper of millions of data points, ensuring that your journey is not just fast, but the safest it has ever been in the history of human travel. Because in the world of modern aviation, the best surprise is no surprise at all.